Well, thanks, Jocelyn, for the introduction. Thanks, everyone, for coming. I'm glad to see you here. So what's actually happening is my colleagues are in the room in the back. So if you want to use the time to talk to someone face-to-face about your own particular thing, now is the time to go grab them and get them solve your problem for free. Otherwise, you can stay here and look at something that I put together, which is an attempt to show you how you could use an existing application. In this particular case, it's a movie streaming platform. No, it's not Netflix. And add some features to it using things like semantic search and all the AI stuff that we currently are so happily putting everywhere where it belongs and it doesn't. So I'll talk about that for a while. Hope that's going to help you kind of establish a mental model of how you can apply that in whatever it is that you're working on. Here it is. It's called PineStream. It's a demo application. Don't expect too much. But basically, it's a sample app that represents a movie streaming platform. You can do a few things already. You can browse some movies. You can see we have a few pages of movies. It can even do things like search. So right now, what is implemented and works in that application is what you would call the traditional search. You put a phrase or a word, and it finds things that contain that word. It can show movie details. So you can click on a movie, and it shows you some more stuff about it. We have full plots about the movies. That's going to come handy in what we're going to demonstrate later on. And you can mark movies as watched. So that's something that we will take advantage of later on when we try to build a recommendation system. So there's a few ways to do that. And then you have the user profile where you can actually see what movies you have watched in the past. Now, obviously, the system is super complicated when we have one user. So everything you see here is like for that user, but it's just for demonstrating the purpose. All right. It also have an administration panel like this, which tells you we have 500 movies in our database, 3 watched, which is what we marked recently. And we have this dense and sparse embeddings, which we will talk about in a second. Now, how that looks like from the back, from code. It's a web application written in TypeScript, Nuxt in particular, Vue.js, for it doesn't really matter what is your implementation. And it comes with a front end, which is like pages and components and all the visual stuff, which I'm not going to bother you with. And it comes with an API. An API is basically what you would implement normally in whatever is your favorite language. In this case, is also TypeScript. So it also uses Pinecone behind the scenes now because we want to add some cool AI features. So how do we use Pinecone? We have this particular library here, like that file Pinecone, that creates 2 indexes, one for sparse and one for dense. And we use the TypeScript API that Pinecone provides to connect to the Pinecone, providing our own API key. And we do call this thing ensure indexes exist every time, so to make sure that whatever call comes in, we actually have indexes. If we don't have the indexes, we create them. And this is how we do. So as you can see, I don't know how familiar you are with Pinecone, but one of the cool features about Pinecone is you can create indexes that are tied to specific models. So then you can interact with the index with text, and it will create the embeddings for you. So you don't have to do embeddings yourself. So those are the dense index uses multilingual lingual E5 model, and obviously for sparse using our own Pinecone sparse English. And if I go to the admin panel and click on create dense and create sparse, what you will see is that it will immediately say it did. It did create, it did process 0, and we have 0 in the Pinecone. And that's because we haven't implemented that functionality yet. So that's the first thing I want to show you, how to implement that. And our code has placeholders for this. So if we go to that file, that's called generate dense embeddings, there's a placeholder here where we're going to implement that. So what we're going to do first is, what the application does is it's going to call this function that's called extract chunks. So basically, it's going to get all the plots and the information we have about movies and chunk them into smaller pieces. And then it's going to call that function, says upsert chunks to Pinecone, which is going to upsert those chunks into Pinecone. So let's do that. So the first step is to actually get the chunks. So for that, we're going to use the plots and the overviews of the movies, and we're going to combine them together. And then if we have those, because we don't have those for all the movies, we're going to actually split the text and then call the chunks. Now, we're going to do this one more time here for the overview. So the first step was for the plot, and this is for the overview. And we're going to quickly go through the code. So what happens here is we use this function called split text, which comes from a library known as LangChain. How many of you are familiar with LangChain? Few folks. So LangChain is convenient in that sense that it also has text splitter. So we are using a text splitter here that splits the text into 1,200 character chunks with, 300 characters overlap. So we basically kind of, from every movie plot, we create smaller pieces of textual data that we want to convert to vectors and store into Pinecone. And that's what we do here, is build these chunks as, in this particular case, TypeScript objects. And we also put there some information about what is the title of the movie, what is the genre, and things like that for each particular chunk. So once we have those, we have to store them. We have to send them to Pinecone to persist them. And this is what this other function does. The reason this function exists is because we're doing this also in chunks. Like, there's like a limit of how many you can do at a time. So the application calls that function with passing a smaller, so we could have like thousands of chunks, but it passes like smaller chunks of chunks, so to say, to upload them. And we just connect to Pinecone, prepare that whatever API is, and then send that. You can see we're using the upsert record function, which is sending text, not vectors. So nowhere here we're converting text to vectors. It's just sending the text, and the embedding model is going to do that stuff for us. So one final step in here is we're going to store locally information about locally in our database, information about which chunk is to which movie. And you'll see why we need that later on. And now, if we go back to our admin API and we click on the processing button, what you will see is that it takes some time. Obviously, this is a little bit faster than in real life, but it processed 500 movies and created 2,000 chunks out of this and stored them in Pinecone. Good. Now let's do the same thing for the dense embedding, and that's another file, and the process is roughly the same. Sparse, sorry, thanks, Ray. The sparse index, so we have the same situation. We have a function that extracts chunks and the function that upserts. Now, what's the difference here? And you'll see that in a while. First, obviously, we're going to get the plots and the overviews, but then we decide not to chunk those. And the reason is dense indexes work differently than sparse indexes. Dense indexes extract semantic meaning, and sparse indexes are like lexical meanings. So we actually care about the words in this. So it doesn't make, you can think of it kind of like counting the words, even though that model doesn't work that way. But like oversimplifying, all we care about things is like what words appear in that text. So chunking this into smaller pieces doesn't make a lot of sense in this particular case. So we're just going to grab those the plots and the overviews and use them as a whole for the sparse index, right? And then upserting is more or less the same operation. We just go get the client and send it, and that's it. We're done. So we can click on now create sparse embeddings, and we'll do that for you, and will tell us that we have 1,000, which is exactly 2 times the number of movies we have. So we have an entry for every plot and every overview of every movie, right? Cool. We have some web embeddings in the database. What we can do now? Now we can actually start doing the stuff that I was promising you, which is adding cool AI features to our application. And the first simple AI feature is recommendation. So if you scroll down the PineStream application, right in there is the panel that says, we recommend these movies for you. The reason you don't see that panel is because we haven't implemented that functionality yet. And that's what we're going to do now. All right, so we go to this file that is called recommendations, and there's going to be some placeholders for that as well. Now, how do we do recommendation? Like, what is the logic behind that? Well, first, we need to find, based on what we're going to recommend something, right? And in our cases, that's going to be what that user has watched before. So we need to get their preferences from somewhere. We know what they have watched, so we can extract that from there. So we get from the API, from the user service, we get what movies they have watched before. And now we use that service, that information that we stored in our local database to know which chunks belong to which movie. So now that we know what movies they have watched, we find the chunks that belong to those movies. And then we go to the next step, which is go to the Pinecone and grab all the vectors. Now we don't care about the text at this point, we care about the vectors. So we get the vector representation of those chunks that belong to the movies that the person has watched. Now, but first we also want to know what is the dimension of the index. And luckily, Pinecone API allows us to get that information, so we can grab the dimension. Then we get the vectors from the database. And then we build something that's called centroid. How many of you know what I'm talking about? None? 2, 3? Cool. Okay. So what a centroid is when you have, so you know what vectors are, I assume. So every vector is like a line of numbers. So you have like so many numbers in the line. So you have many vectors. You want to build a centroid. You get the numbers at the same position. So the first number of every vector, and you make the average of that. Then you get the numbers at the second position in every vector and make an average of that. And then the third, an average of that, and blah, blah, blah. And so that's the reason we need to know the dimension. So we need to know how far we go in the vector space. And then whatever comes out with those averages is your centroid. And it's, in logical terms, it represents so if every vector represents several characteristics, the centroid represents the average of those characteristics, right? And so what we're trying to do here is trying to find the centroid. Once we find the centroid, we're going to use that to find other things that are like this centroid. So first step was to try to figure out like how to represent users' preferences, so to say, in a common way. That's why we built the centroid. Now that we know that, we try to find what else in our database is close to the user's preferences, right? And that is basically calling the index and asking, give me the things that are close to the centroid. And what it's going to give us, chunks, right? Because that's what's stored in the index. Now, so once it gives us the chunks, we need to figure out what are the movies, what are the highest ranked chunks, like what are the closest to that centroid, and what movies they belong to. And once we figure out what movies they belong to, we can actually do this, clear the watch list, just so that we have some more movies, and we all run them out 10 movies that user has watched. And what you'll see, it's like, yeah, they like crime and comedy. Cool. And then once you go back to the home page, you'll see a recommended for you section, which based on, and it's going to say up in the corner, based on 10 watched movies. So those are the 10, based on those 10 movies that the user watched, we now recommend those, right? It should fit their preferences, right? So that's the panel. So, hey, simple AI feature number 1. Now let's do another, semantic search. So you saw already we had a simple search, but how about we want natural language search? So here's a search with like a phrase. I watched a movie in the 90s. It was about this. Like, find me that movie. Well, it doesn't find anything because it's not there. We haven't implemented that, and we will do now. So there is, of course, a placeholder for that thing also. And it's that function that's called do vector search. Now, that function is actually called by the system twice. The reason it calls twice is because it uses two different, every time it's called for a different index. So you can see it accepts the text that we're going to search for, the limit, how many things we want to find, the metadata filter, if we want to have one, and the index name. And so we're going to, what the application does is calls this function twice for both the sparse, once for the sparse, once for the dense. Now, the reason we can do that is because the API, Pinecone API to interact with those indexes is the same. It doesn't actually make much difference whether what type of index you interact with. So here is the logic. So we have a search query. We construct, and then we just do index, whatever the index is, sparse or dense, depends on the call. Search for records with those search options. And we specify the top K and the actual text. Now, again, notice that we are searching with text. We're not converting text to vectors, to pass vectors, to find similar vectors. We're relying on Pinecone to do that stuff for us, which is super convenient. And once we execute this, we get the search result, and for each, we find the movie ID because we have this in the metadata, so we know which movie that chunk belongs to. And then we do, on the most important part of this, a rerank. Now, why we need a rerank? Because we run two things. We run search against the sparse and search against the dense. And so the search against the sparse says, like, those are the movies that match the query. And so the other search. So now we have two sets of results, and we need to figure out we need to merge them. So what we can technically do is just merge them together, eliminate duplicates, and said we're done. But a better way to do this is to actually send them to a reranker and say, okay, we found these movies, and we want you to tell us, and this was the original query, and now we want you to tell us which of those are actually more relevant to the original query than not. So we're going to use a reranker for that, and that's the get highest ranked movies function. And in here, what you will see is that it gets a list of all the movies. No, actually, it gets IDs. We get the movies from the database by their IDs, and then we create this text from the overviews and the plots of the movies. And then we call again, through Pinecone API, we call the rerank function. And in the rerank function, you see we pass the search text and all the text of all the movies that we found. And what we get is a result that is what movies are actually more related to the result, to the original query the user had, than not. And so once we have this, our semantic search starts to work. So we can search for comedies about family relationships and coming of age. And it actually will go and find some movies related to that. Here we go. What is even cool is that we can now use the reranker results to show how similar those results are to the query. So according to the reranker and some math, why him is like 14.9% similar, whatever that means. But there's a problem. Can you spot the problem? Here's the problem. We're searching for comedies, and it found us horror. That's probably not what we want. And then that's one of the things that when you actually try to extract semantic meaning, things that are like semantically similar words, but like lexically classified things can slip, right? It didn't notice that this is a horror movie for some reason. Right? So what we actually wanted, and if you try to do the same thing with dates, it's probably going to be off chart as well. It would be really hard purely with like dense search to limit that. Just give me the movies from that date to that date. Right? So when we get into this, what we actually want is to use how's it called? Blanking on the English words now. Structured data. So when we have that data in the metadata for all the stuff that we've indexed, so we should actually use that. But that means we need to either ask the user to provide both semantic query and metadata, or we need to somehow, from their textual intent, figure out how to apply metadata, things like categories, gender, genres, or date ranges, right? So we can do that actually, and that's what's known as query expansion. So there's this function. It's like get search insights, and what the application expects from this is to get a search insights object that tells the application what's the user intent, right? Other than what they expressed as a query, right? So right now we're returning an empty insight, so there's no extra information. That's why we get the horror when we search for comedy. Now we need to implement that. Now how do we do that? Is, well, we call an LLM and ask it to do it for us. I mean, that's how you solve all the problems these days, right? You just call an LLM, say, that's my problem, solve it for me, right? So we do the same thing here. So this is our LLM system prompt. And we're going to say, hey, your movie query analyzer, whatever, I want you to return me a JSON as a result. And that JSON should look like this. It should contain genres. It should contain date range. And by the way, because later on I'm going to be doing dense queries and sparse queries, it would be nice if you can optimize this query better for these types of searches, right? And then some message for the user and whatnot. So we provide more detailed information about what are the genres that are actually in our systems, so it doesn't come up with things that we don't understand. And we also provide instructions about how to handle dates. So if the user writes something like 90s, consider that to be from 1990 to 1999, right? And things like that. And then we provide some information about how should it convert that very expressive query that the user wrote, or very short one, into something that is better suited for dense or for sparse, right? And so that's like a long system prompt for the LLM, telling the LLM what to do. Once we have this, we're going to use what is it? Llama 3, 1.8 billion parameters LLM, and we're going to pass the system message we crafted and the whatever user is searching for, and we get a response from the LLM. And if the LLM is good enough to follow our instructions, that response should be a JSON that we can parse into this search insight thing. Right? Now, the tricky part about this here is, from experience building this, is you're going to have to adjust your prompt to the LLM. Some LLMs are very good at following instructions. Some, like this, some LLMs would want to enforce the fact that you want JSON in different ways and whatnot. So Llama 3.1 works well with that prompt. If you switch to a different LLM, it may not, right? And then once we get the insights, we prepare that object that we can pass then to the search. And the search will then take into account what we have discovered from the user prompt and put that into a metadata filter so that we can further filter the results based on the discoveries that we have from the query. So we can do the same thing again here. We can go to the semantic search and find, run that thing about the time loop thing. And when it does it, you will see, apart from the results, that panel over there that says smart filters applied. And what you can see in there is that based on stuck in a time loop, it figured out that's a science fiction genre. So it actually searched for movies within the science fiction category. And also from the 90s or early 20s, it figured out the time frame, the tags for the metadata should be movies created between 1990 and 2004. So now we have not only semantically searching for things, but also limiting the scope based on actual tags and metadata. Okay, you can actually expand that a little bit, and you can see what else it returns. So it gives you the date range and the genres, but it also gives you the actual dense and sparse queries that was suggested to use. And that's indeed what we use after we get the search inside object, and we call the dense and sparse indexes. We actually are using this stuff, not the actual query that the user wrote. All right, that's the cool AI feature number 3, and let's do the cool AI feature number 4, which is similar movies. So if you open a movie page, you see a big blank spot on the right, and this is where we want to display, like, oh, you're looking at this movie, but maybe you want these other movies which are somehow similar, right? So for this, we need 2 things. We need to find and retrieve those movies from the database or from somewhere, right? And then we need to explain to the user how are they similar, right? Because otherwise we could just randomly grab some movies and say, oh, those are similar. Like if we don't have to justify why they are similar, right? It just makes no sense. So we have like 2 phases. We have a retrieve phase and a generate phase. And of course, we're going to ask someone something to generate it, right? So we need to augment that request with what we've found. And that's what traditionally is called RAG, retrieval augmented generation. So that's what we're going to do now. That black spot is going to have our recommended movies. And here's how we implement it. So that's, again, a function that does exactly that. It retrieves similar movies, it's called, and the only thing it gets as an argument is the ID of the current movie. And so the first step is obviously to get information about that movie. So we get the plot and get the overview, and we get the genres, so we can scope and search in the same genres. We combine those two into a single query, prepare the metadata filter, and then we decide at this point that we're only going to use sparse for this, because if they're similar, they should use the similar set of words, right? So we're not looking for semantic similarity, but more of like similar in the textual sense. Like we could do this with dense as well. It doesn't really matter. Just for the case presented here, it uses sparse index, right? So we just call the sparse index and say, find me things that are similar word by word to that thing. And this also saves us the trouble of like doing multiple chunks and whatnot, which is convenient when you're doing a demo and you don't really care about the end result. Don't do that in real life applications. And so then we find those top matching movies, right? And that's pretty much the retrieval part. Well, one more step in here is we need to kind of figure out if there are duplicates, because we still have two chunks from the overview and the plot. So maybe there are more results than we expect. So we get the top 10, and then we get the IDs, and that's it. And if we go now to the page again, you will see that it renders similar movies. That's the retrieval part. We found which movies are similar. Now, how are they similar? Well, they're similar in genre and style, whatever that means, right? So we don't have a good explanation at this point. So we need to do the generation part to actually compare those to generate an explanation of why they are similar. And so this is what we're going to do with the generate similarity description function. So it gets the movie and it gets the similar movies that we found, and then it will ask an LLM. Surprise, surprise. Right? And so we're doing the same thing. We are asking the LLM to generate us a description of how these movies are similar, right? And to do that, we need to pass to augment the request with the information that we found, which is the similar movies and their plots and overviews. And so this is basically the system prompt explaining that to the LLM. And then down below, it's our user prompt. And this time, our user prompt is much larger than the system prompt, because it will contain the plot of the current movie, right? And then it will contain the list of all the movies that are similar with their plots and stuff like that. And then we can call it and get the result. And in this case, what we're using, again, Llama. And then we get the result, and then we split the result. We basically told it in the description that we want all the comparisons in new lines. So we just split it by new line, and those are our responses per movie, per similar movie. And then when you do that and you go back to the same movie and reload the page, you will see some explanations. It says now that Don't Breathe 2 is similar because of both films involve complex and troubled, blah, blah, blah. And then for all the others. Now, if you expand those, they're actually longer. I'm just cutting them off because of the screen space. But it depends on how you instruct the LLM. It can generate more or less information. And with that, we just implemented 4 simple AI features in our application. I hope this was useful. I kind of rushed to it because I didn't want you to spend too much time on analyzing the code. But the recommendation, semantic search, query expansion, and the RAG use cases in that application are all available to you at that URL. That application is something that you can actually download, run, explore, do whatever you want with it. So if any of those things are like the things that you would at some point need to do and you want a reference point, feel free to use that as much as you want. And of course, if something's not working or you have more questions or you just want to tell me that I did something stupid somewhere and should fix it, you can always reach me at, well, I only put my Blue Sky, but my email, you'll find it on the website, so, or through Pinecone, whatever works for you. Well, thank you very much. That was the presentation for today. I think the plan was to now have a Q&A. Who should I invite on the stage? All right. Jenna, you want to join us? And now we are all yours. Ask questions about the presentation, about Pinecone, about anything, right? Whatever's on your mind. Who's going to go now? Here you go. I will repeat after you so they don't have to shout.
My name is May. My question is like breed specific. I'm curious what kind of indexing strategies you guys use on your vector embeddings, or is that proprietary?
The algorithm itself is proprietary. It's like a variant of a proximate near neighbor that's really efficient and low latency. So we find that people see benefits at the million billion scale.
Very quickly, is this very different from Postgres RPG vector?
Yes. So many vector databases use HNSW, which requires you to rebuild the index every single time. We don't need to do that. As soon as you put a vector in our index, it is very fresh and available. That's part of the benefits of using our platform.
There's a different ways of searching, but it's good. Yeah, go ahead. Don't worry. That's the reason why we're here.
Because I was like working on this a very similar thing like some most different from the like IBF flat, vector embedding from PG vector, because that's what we're using right now. We also just like create centroids all time. And,
So a lot of the question is, how does our indexing algorithm affect like people's user experience when they're developing with Pinecone? So a lot of the problems that the thing about indexing algorithms is that they start mattering when you work at the billion scale, right? So when you have a user document, hundreds of thousands of users, you have hundreds of thousands of items, required descriptions, the type of approximate search that you're implementing starts to matter a lot, because you could figure out what is semantically similar. Well, you need to not search every single vector index, otherwise you're going to be way too late and the user will churn and they won't watch a movie on Milen's great application. So part of the concern at that larger scale becomes the indexing algorithm. At the smaller scale, a lot of people want to build quickly and effectively. We find that using Pinecone kind of helps people kind of do that without having to think about what algorithms to pick. So very often with other vector databases, you have to pick your indexing strategy. You have to kind of keep an eye on it. You might even have to allocate servers to address how often people are querying the index. You don't have to do that with Pinecone, and that kind of lets people build pretty quickly.
ICC, you guys kind of like abstract away the complexity of choosing your strategy and all that.
Exactly. So our goal is for you to not think about the indexing algorithm at all, because you have the confidence to get the relevant vectors at scale. Your name is... Nice to meet you. What's your question?
So the source data that you're using is basically the description of movies, as far as I got it.
Sorry, repeat that.
The source data that you're using for the recommendation is basically description of the movie.
Right.
So basically some text, yeah.
Yeah.
Would it be possible to also do like a search, see, find similar scenes inside of movies, like of like a 1.5 long movie, and just like figure out, let's say I like the scene of this movie, I want to find out like the movie with a similar scene.
Yeah.
How do you do the chunking there?
Right. So the question is if what was presented uses textual descriptions like plots and overviews, and we search between those and find similarities, would it be possible to do the same thing but with like video? Like so the user, I assume, uploads or points to a fragment of a video of a scene of a movie and would want to find a movie with similar scenes, right? It is totally possible. It's just not that easy. And the reason is, first, well, so all the things that we have here naturally work with text. Like even Pinecone internally, we have embeddings, hosted models that can convert text to embeddings. We don't have hosted models that can convert videos to embeddings. Yeah, well, you can do that. That would be the exact, like, the question is, what about books? I say that's the same thing as here. Like the plot here for the movie is about 2,000, between 2,000 and 5,000 characters, depending on the movie. If you have a book, it would be like in tens of thousands or hundreds of thousands, whatever. The only difference from what you saw would be that you would have a lot more chunks. All right, and then
Figure out how to chunk it.
yeah, you need to figure out like what makes sense, how to chunk a book, right? Whether that's going to be per chapter, per page, there's like tons of different strategies, but technically it is the exact same approach for as long as you work with text. Now, back to your question about working with other types of data, like images or videos, you can do that, and there are models that can convert those into embeddings and compare and find. But then that's at least currently with what we offer at Pinecone, that's the part you would have to do yourself, which is you will have to figure out how to convert a fragment of a movie to a vector embedding. Then you would have to go through all these movies and have them have their videos, which means you would probably have to have some sort of contract with the right movie producers and whatnot that convert, chunk the movies into small pieces, like vectorize those. It's not impossible. And then conceptual, it's not much different. It's just much harder to do, not only for technical reasons.
Dallas video embeddings as a service. Did a webinar with Ted recently that showcased what he described, scene detection and pulling flips out. The other thing I want to touch on that we mentioned is we talked about what happens when you chunk the data and kind of put it into Pinecone. But in this use case, you'd have to deal with the retrieval as well. So when you retrieve, you're going to get a bunch of chunks back, and you have to kind of look at the metadata of the chunks to turn them into books. So you could say like, hey, 10 of the first chunks are from the same first 3 books. Those are the 3 books I'm going to recommend. So it's kind of like a hierarchical search. I'll have to show back to you. Great question.
Yep.
So for your example, could the dense and sparse indexes, when you created those, was that Pinecone's embedding model that you used by default?
So question is, for the sparse and dense, was that the Pinecone embedding model? Yes. So for the embeddings, for the actual conversion of text to vectors, those models that do the embeddings, they're hosted by Pinecone for this particular case. Right, so you can do both. You can create indexes at Pinecone and say, I'm just going to store vectors. So I don't want anything to mess up with them. I'm going to produce the numbers, the vectors myself, right? And then you can use whatever embedding models suits your use case. Or you can say, I want things to be convenient, so I'm just going to send you text and you do the conversion for me, which is what I'm doing here. But it's not that you're not forced to do that. It's a convenience, not a requirement.
Very ingestion for people, like the whole chunking and then embedding and then storing. What I've seen you very challenging, especially for folks in the agentic space, is the actual retrieval and query pipeline at scale. I wonder if there's any problems you guys can mention about that and solutions you've seen that folks use in the space so far.
So the question is,
folks handle like context loading and retrieval from vector databases at scale.
what's the best way, quote unquote, to do context loading and retrieval at scale? No? Okay. Who wants to take that?
Could you tell us more specifically what kinds of applications you're thinking about? Like for an agentic application, you could be really heavy. So you might have a lot of queries, like a deep research kind of thing. Or you could be accessing data from a lot of different databases and kind of have to figure out which one's more relevant. So like, what are you thinking about?
So let's say either deep research or just a typical application of pulling from a company's knowledge base. Like a a customer service agent, for example.
Okay.
John, I want to go.
I'm curious to know, like, where do you see like the bottleneck in the tree?
So when you have a very, very large data, you can't do skippable RAG. Like you have to go and refine the query. This is what I'm seeing. I'm curious if there's other strategies. Is you have to refine the query first of all. Like they'll tell you, oh, find me the best customer for this. And that isn't a good enough prompt. Trying to have a second guy go and rewrite that prompt. And then from there, do multiple different queries on our database over and over and over again. And then have like a third agent go and refine that. And then that one or a fourth agent goes and then pipes that back in a useful format for the response agent. And that's one pattern I see. I wonder if there's more than that though. And if there's something that we're not seeing, because you guys are the experts.
Sure, absolutely. So the pattern you're describing is similar to what we use in our assistant product. Yeah. So what happens is you have an initial user query. You've preloaded a database with like tens of thousands of PDF files or whatever it has to be. And yes, the user passes in the query is very vague, can't do much with it, right? So you kind of have to do a query planning step. So what is this user trying to actually answer? Create a set of subqueries, fire them all off. You get a bunch of different results back, re-rank them, so on and so forth. If you're looking for like an in-production example of how to do this pretty well, our assistant product kind of has a simple kind of structure to kind of answer that, to be able to do that. I think if you're trying to think about how to improve beyond that strategy, which I think is pretty good, you probably want to start at the query level. So you need some information about what your users are doing, what kinds of questions they're asking, what are they not actually retrieving, and that will give you information about how to expand the query like Milen did in his demo. The second part after that people have a lot of difficulty with is properly informing their agents of the databases that they are linked to. So often, in many guides and examples, we'll see people make tool calls to their database, but they'll fail to give the tool call sufficient context about what is inside the database in order to retrieve the appropriate context, right? So if you're building an agentic application, you write a query, you say, hey, make this query better, and it writes a bunch of stuff that doesn't really make that much sense in the context of what you're doing. So it's important to kind of inform your agent what's actually in your database in order to make that retrieval make a lot of sense. Finally, the other thing you want to think about is the amount of information you're retrieving and whether or not it's relevant to the agent that you're building. So we find that re-ranking is a pretty essential step if you're building a deep research type application, because the amount of chunks that you're going to retrieve are so different. And on top of that, the meaning and importance of those chunks are going to vary across the different queries, right? So you need a step that kind of agglomerates the different chunks that are being returned with respect to the original query, in addition to how they should be arranged with respect to one another. That's going to get you most of the way there. Everything else are strategies that you have to implement, understanding what your users are doing and failing or succeeding at. It's kind of hard to generalize beyond that point. But we see people kind of implement things along those lines. Right? Mm-hmm.
All right. Yeah, go ahead.
Do you have any advice around like you're selecting embedding plots? Like I've seen like there's like multimodal models now that like you can kind of get image of, let's say, a PowerPoint library.
All right.
Capture information versus going through the work of like extracting text and then doing the chunking, stuff like that. It seems a lot easier just to like.
All right. So the question is, do we have any recommendations around embedding models, and particularly with the fact that we now have multimodal models, and should one use those, or do different types, like split the different types of content and then use models dedicated for a particular type, like data, like text or images or something. Did I understand correctly? Yeah. Anyone? All right. So, so the answer is yes. I mean, like, yeah, the answer is yes. I mean, like, no, that a lot depends on what you're trying to achieve. So, in a lot of scenarios, multimodal models will actually do a good job. And in a lot of scenarios, it won't be the result you're expecting, right? So it's really, to me personally, it's kind of hard to say. Now, the other thing is all those things are constantly evolving, right? So whatever I say today, it may be not true 6 months from now, right? Because there may be like 100 times better models at that point. So I've been actually having an argument with Arjun some time ago about similar things. And basically, we came to the conclusion that the only way to know is to evaluate and test and figure out what works. Because it may vary a lot from use case to use case. And even if we were to give you like 3 to 5 to 10 use cases where one approach definitely works better than the other, there's no guarantee in your 10 use cases that's going to be the case, right? So the answer is yes.
Yeah, things change pretty quickly. So like whatever advice we give you now may no longer be relevant. I've actually worked on the problem you're describing, which is you'll have like webinar slides or videos or whatever, and you want to kind of deal with the multimodality in that data, right? People are speaking, there's things on screens, things kind of change over time, right? So on and so forth. I think conventionally you're going to be compute constrained, right? So these multimodal models are more expensive for you to represent everything in the same embedding space. And you're sending data that's larger back and forth with whatever API that you're using. So if you have images, you're going to send that whole thing back and forth versus if you just have text, or if you have video, then it's a whole bunch of images that kind of send back and forth. And at that point, you're kind of constrained by latency. So typically you want to use something that's kind of faster, and the text models are pretty fast. But like Milen said, that might not be the case anymore. You might find an embedding model that's pretty performant that no longer is the bottleneck. And in that case, you'll only know if you try using it.
And also, if you do it on your own, so let's say there's a video, like I'm making up an example here. Let's say there's a video of something, then we could either and then it also has, like in my slides, something moving and text and things like that, right? And we want to do that. So one thing is you just send that to some model, say figure it out, right? And it may figure it out quite well, but you could but it may not. If you are looking the nuts and bolts and need to nitpick something on the slide that was moving, on particular movie image that I was showing in my presentation, it may not be that detailed, right? So you may want to say, okay, I'm going to split that. I'm going to extract it. I'm going to use one thing to extract the text. I'm going to chunk the video into smaller pieces, then extract images from that, and then I'm going to extract more from that images and convert it to text description of the images and send that. Then you interact with text, so potentially you're paying less and your latency is better and whatnot, and potentially you even get better results. But then when you get the results, for a fragment. Now you have to go and stitch it all together, to know where, at which minute in my presentation, that thing that you found in a text description of an image that was a screenshot of the presentation was taken, right? So the process of like reverting back to assuming you want to find that, right, may be too complex. So that's the reason you cannot give a definitive answer, because like the complexity of doing this varies from relatively simple to like super complex. Depends on what your requirements are. Yeah.
I will give you one pro tip though. One thing I like doing is transforming everything to text, doing the retrieval in text, and then once I'm ready to get context to my downstream LLM, I pick a multimodal one and then make it multimodal at that point. Because then you're not having to deal with like using all the different embedding models until you absolutely have to bring it to the LLM.
Yeah, go ahead.
The question about reranking. In one of these cases, you mentioned you would retrieve
That's
right, and combine them and use the ranking to reorder.
yes.
I suppose the ranking meaning relevancy to the question.
So rearranging the result.
That is not
Right.
would be that done.
Right.
With respect to my origin.
Mm-hmm.
How do you what's the logic?
So your question is essentially how re-ranking works. Yeah. Okay. You want to take that? You want to?
Sure, I can.
Yeah. Okay.
So the cool thing about vector search that you're kind of extracting the concepts from your query. You're extracting concepts from your documents, and you're saying, hey, find me all the concepts that are similar to this input query, right? But the trade-off that you're making is that the query doesn't know about the document. And the document doesn't know about the query because you're embedding them separately. And so the motivation is that because you're looking for this relevancy separately, you can find things that are relevant enough, semantically similar enough, for you to kind of deal with the results initially. And embedding models get really, really good at kind of doing this. But because you're embedding these things separately, they don't have context of each other, you can only get so far in certain applications where you need relevance in addition to semantic similarity. So something can mean something similar to what you're interested in, but not be relevant at all. So you can look up information that could be similar literally to the words that you're interested in, but not be interesting at all to your query. That's where re-rankers come in really handy. And the second situation in which re-rankers are super helpful are when you have two different retrieval methods that are scored on different axes. So sparse retrieval has a different score assigned to each of the results than the dense retrieval will. So we can't compare the scores in the same space because they aren't derived from the same space. So we need another model to calculate another score that's keeping the queries in context of each of the documents. Then we have one score, and we can reorder all the documents with respect to that. So we do a pairwise computation. You have your query, you have a single document, you pass both in the same context to a model, and it outputs a score. And you do that with every possible pair, query with every single document. So in this case, in your example, you do 200 steps, right? Or 200 scores, right? And then you just reorder everything based on that.
Using the re-ranking model.
Using the re-ranking model.
And that's essentially what the re-ranking model does. Like that's what you saw in the demo. What I did in this particular case, what the reason I did it was the second reason Arjun described is because I have results from dense and I have results from sparse, and I do have weights or ranks or whatever you want to call them for both. But I have like 5 here and 358 here. And there's no way to compare them because they mean completely different things, right? I can both list independently. I can order from the most relevant to the less relevant, but when it comes to merging, I have no idea whether they should be like this or in between, right? And so the only way to do that is to get all this and send it to a model that's trained to compare things. And says, hey, this is what I have. This is what is supposedly like this that I have. Now tell me how close they're to each other. And it gives me a score, right? And then if I do this for all the items, now I have used the very same approach to, I can compare the results. If it tells me this is like 5 and this is 3, I know this is more similar than this because they're all using the same metric.
One more example, just to kind of help think. Imagine you're taking 2 different classes. The professor in each class grades your exams on 2 different curves, right? If you take a set of tests from one class, take a set of tests in the other class, and you look at what letter grade they got, you can't really understand how to compare them because you don't know what the distribution of those letter grades are in those separate classes. So you kind of need a way to combine those scores into one new score that is actually comparable, right? In that case, it could be an average or a weighted average. In our case, we're using a sophisticated model to compute that score.
And that's the re-ranking.
Yeah.
Where do I get that re-ranking?
Pinecone. We got one.
Yeah. That's one of the things that we offer. So yeah, we do have a re-ranking model as a service. So you can, and that's what I was using in the application. So that call re-rank actually calls Pinecone, sends the data to the re-ranking model, and the re-ranking model returns the results. Now, if for whatever reason that model is not sufficient for you, there are other re-ranking models out there that you could potentially use from other providers. But from what we've heard so far, the one we host does pretty good job. Not all at once. Yeah, go ahead.
Can you speak a bit to your invalidation strategy? So in the case that there is embedding created from data that is in contradiction to another embedding, like how would we go about that failure?
By contradicted, like what is the contradiction occurring? That necessitates the update?
Like let's say we have created an array from dogs. All dogs are red, and then he got all dogs are blue. How do we go about?
I see what you mean.
Yeah.
So you basically want to what you want is you want to invalidate previously embedded information based on new information. That's what. Okay, I don't think that's an embedding problem. In a sense, like you could technically you could do that by well, like conceptually, not technically. Conceptually, you could do that by first searching for the opposite of your new findings, right? Finding those and remove them, right? But the whole idea of like how not similar something is I think it's like error prone on its own. I mean, you gotta correct me if I'm wrong here.
There's harnessed, right?
Not an operation like you could.
Right, but in this particular example, if you have a statement like dogs are red and then dogs are blue, like those not going to be the furthest. They're going to be other things that are much further, right?
Or in what context have you seen?
Yeah, where you see like these two statements that's the other. So yeah.
Carlos, in for this use case, we are grabbing data from Slack, or you were using data from Slack. And so if someone writes a message that essentially invalidates a previous message, how do we update the vector database?
Are you trying to figure out what that previous message was?
No, we're trying to update the vector database so it reflects the true state.
Okay, so this is more about like the truth of the information located in the vector database, right? So you have an update to a previous idea.
Yeah.
How do you find the incorrect idea, remove it, and replace it with the correct idea?
How do you know when the thing is true?
In your example, I would use recency, right? So somebody has a message like, this is the time and place for whatever, and then the new message comes in, it's like later in the earlier one. That's an easy heuristic kind of use. But I agree with Milen here. I'm not sure that's a way you can resolve using embeddings. I think that is more of a what is the context?
I think in the Slack example in particular, what like how honestly I don't know the answer, so don't take it like I'm giving you the solution here. But if I were challenged with that, my first approach would be to time frame it and scope it and reason about it in particular scope and time frame. So they're going to be chat or channel or a group of people in like, I don't know, whatever hour, day period and whatnot, and just get that data and try to figure out how to reason about that, and then only update your source of truth after that time period has expired, after you've been corrected. But I don't know if that solves the problem that you have. Corey has.
So there's two approaches to the problem, and then both about timestamps. So the first one is every time you create new embeddings from a Slack message and store function, part of the metadata needs to include the timestamp when that message was created, right? That's key. So then what you do is you either, when you do your retrieval, you look at the timestamps and in the business logic of your application, actually reorder the relevancy based on recency, as Arduino's date to. Or you send the whole context to the LLM, including the timestamp to prompt saying, way more recent answers have.
Yeah, but that you can do that, but that assumes that your
assigning truth based on recency. Yes. So the question is, for your use case, are you asking, like, are you predefining what's true? Meaning, are you saying dogs are, like, we know dogs are blue, but somebody said that dogs are red. So how do I figure out which is which? Or are you just saying,
The most recent.
like, yeah, you know what I mean? Like, do you have a predefinition of what's true? Or are you asking the database to tell you what's true?
No, in this use case. I think recency will suffice.
Yeah, okay, and that's, yeah.
Yeah. Good question. Very interesting. What about if you don't want to get rid of the thing that's been invalidated? Because if somebody would need to be able to know what existed before, in case that's, like, for example, let's say someone is using this information up on Slack, and then they're working in the code base, there's like a plug, there's some question, and it's like having information about what was true will help them, even though it's not what's true now. It's like knowing that it used to be true would still help. So then, like, what if you don't want
That's right. Yeah. So you're not going to filter against it. You're just going to order by it, or tell the LLM again. More recent is more accurate, right? But you're still going to send that context. So it's going to know that at some point in the past, Alice said the dogs were blue, right? And then more recently, Bob corrected her saying, no, actually, dogs are red. So the model is going to take that context in that order and understand from prompt that Bob's statement, he has happened more recently, is closer to the presumed truth.
So what you're saying is that the model that's actually going to be take that to know to be a response.
Correct.
The prompts of that model, you'll be able to say that more.
Exactly. Correct.
So that would be like, if it's a system, it's one application.
Yeah, this is part of the, people call it a prompt engineering, right? It's about constructing NLP instructions that get sent to the LLM, tell it how to interpret the context that's being sent and how to return it, what tone, what voice, what manner.
So,
possibilities. It's not. So
Elements are stochastic, so there's always a chance that there's a non-zero chance that it'll give the wrong answer, even with additional context, right? The more systemically constructed your prompt is for your application, the less likely it is that it'll run into that kind of problem.
Is that yeah, okay. Might be going a bit because it's a basic speed. I guess there's something that you'd be able to be with that.
If you have more better context, you get better
That context, and I think what he said, right, the prompt and the application. So for Pinecone, for our application, the prompt is really specific to the knowledge base that it has. And that we say, like, yeah, we guarantee this certain accuracy. We have our eval, because we can guarantee the result that we could have Pinecone, right, the parameters. That is very deterministic. That we add any LLM to what he was explaining, either any part of the chain, then you add the availability, and then your evals change based on that. So I think going back to the use cases matter, how do you determine, right? So in our use case, we have made it a norm that anytime there's a new regulation, we will delete the old vectors, and the vector database will only have the current regulation. That's a part of the decision we set. And we basically asked, like, do you really need the history of the old replication as your people? The answer was not really. Now we're grappling with, like, board meetings at a local city level, right? And those are dozens of board meetings since 1970s, or maybe one query. So discussion, like, we have everything in, like, properly in a vector database, but those board meetings are drowning out regulations. So now we are challenged with, like, okay, well, if they don't need to get access, goes back to the user experience. Can they be accessed on the
So, and it also, like, the more I'm thinking about it, it's also like we're going into like an LLM world, which is like not really where the original question was about embeddings and stuff. So there's not so much you can do with embeddings. Like when you get the entire agentic flow to play, there's tons of options in there. On a pure embeddings level, the only thing I can think of is to use metadata. So you could, for example, in Pinecone, at least I'm not sure about other places, but you could use like higher than, lower than, metadata filters. And so technically what you could do is, if you at some point you discover a previous information being not that accurate or not compliant to whatever standards you have, you could technically change the metadata for information for something that says this is now less relevant or less important or less true, right? And then when you do query, you could say, now I want to only retrieve information that's above that number of certainty, if you will, or whatever your your measurement is. Now, theoretically, that's possible. You can do that. Now, how efficient that is, and depends on like what's the scale of the data, how far back you want to look, whether or not you can actually limit it by a number, right? So I think those are like the options you have on an embeddings, pure embeddings level. Now, when you get something that is capable of reasoning, that's a whole different story. Right.
Yeah. Like, I think on one more, wait, this is very interesting. So I feel like I should give you one more idea. But a lot of the insights from like how older search engines were built and how people kind of thought about those could be very applicable to your use case. So at this point, I think you can make the argument for looking into the user signal level data to understand the context of the things that you're kind of retrieving. So let's say you have two pieces of competing information in Slack, right? And you serve someone a search and they find both, but they click on one because they're like, actually, this is the correct one. And they bookmark. That could be fed into whatever re-ranking that you do, being like, hey, this piece of information has been bookmarked way more, or hasn't been unbookmarked as much as this other piece of information, or has been reacted to, something like that. That's how like production level RecSys systems work. It's not only the semantic information, it's also who's clicking on what, who's being added to the card, how recent that information is. You have a whole suite of like re-ranking that you kind of have to reconcile and incorporate. So those are the levers you need to start pulling after you solve the semantic level.
Is it possible for re-rankings to be done based on based on tags as well? Like if like define a scale ourselves, the re-ranking based on that's
just sending it all to an LLM.
So
like a re-ranker is just an LLM, right? Okay,
well,
you can stick whatever you want.
Some re-rankers just output scores, but you could have an instruction following re-ranker, which is what Roy is talking about, which is you define the score regime in natural language and you output.
But also it in a lot of cases doesn't make sense because metadata is by definition structured data, and you can just do regular operations on structured data. You don't have to convert it to unstructured and send it to an LLM to do the calculations for you. Yeah, I mean, it's not that you can't. I see you had a question. Yeah. So I'll just repeat the question. The question is, do we have any ideas about how to proactively find conflicting information?
I don't know that I can give you a strategy that I will, but I can give you some ideas that I think make sense to kind of approach this problem. So the first thing I'd push back on is like what kind of conflicting information are we talking about, and like what specifically we're thinking about. Some people see this as like a quote unquote conversation summarization or memory problem, right? Where you have like some LLM that kind of lags a bit and looks at previous messages, extracts like facts, right? And then once a new fact comes in, you compare it to the previous ones and you're like, okay, how in tension is this fact with what I already know is true? And you have to kind of let an agent decide whether to update the new fact, destroy it, or just add it to the pile of things that you're interested in. So that would be an explicit like information management system. Is that scalable when you have like a billion vectors? I don't know about that. Does that make it easy to find information that's directly contradictory? I'm not sure there's an easy way to do that in Pinecone, because we don't return the most not similar information or anything in reverse like that. So I don't think there's a way to fit.
So theoretically, it's like a non-similar thing where the thing that's the farthest away would be like on negative scale of a cosine.
Right, it's like these. So like, I mean, it's very far away when one sentence is talking about cats and the other one is talking about drapes. Would it be very far away?
Yeah, exactly.
One sentence is like cats are blue, and the other one is like cats are red.
Right. So kind of so not exactly right. Like so so if you it really depends on what you're looking at. Like so semantic dissimilarity is one text is talking about cats and dogs, and the other one is talking about brick walls in Japan. You know what I mean? Like they have nothing to do with one another semantically. Okay, if you're talking about like this cat is red and this cat is blue, they're actually quite similar.
Yeah. I would just if we're back to this very far, then mean the inside. That's meaning the side. Like cats. But say cats is red or cats is blue. It's like completely like it's right. It's a different thing. It's like contradiction. Like it's a subject, but it's actually close. But
it's more like you'd have to consider this logical space, not any stuff.
Which is, I guess, close to me.
It's not something that our product Karen and this holds, right? We're not giving you a way to make sure your data is like correct in the context of the application that you're building.
Maybe we should create a product for that. All right. Yeah, go ahead.
I wonder if the Min thoughts there was either involved in a tangentiary on efficient the raster retrieval higher into scale. Is like you have to do a close-up similarity search every day, kind of like since then that gets difficult when you're trying to load an additional context from a graph. I wonder how you see the information being stored and related in the vector database at the graph at scale.
Why does it get difficult? Because you're using the graphs?
Because you have to traverse between just depends on where you enter it. You can query it in the graph directly, or you can query using the convex. Like just go into the vector database itself, and then from there you have to go traverse, cut to the graph, find the related nodes, and then do you feed those in, or do you go and look at other embeddings first? I'm just curious what you've seen in that regard.
So the question is about, I'm not sure how to simplify it, but it's like a graph search, graph rag, yeah. Yeah, the complexity of like doing search with semantic, like vector search and graph traversal, right?
Very happy conversation before. Talking about basically, like a lot of people are interested in this idea of leveraging graph relationships, like that additional about their data, right? Knowing that there's difficulty about vector searches that it doesn't have that relational information. Right? Look at that. On the other hand, just using a graph database is also difficult because it's hard to locate the node that is interesting, right? And B, how to traverse it, right? And so we've done a lot of experimentations on this. We wrote there's some stuff that we wrote on our blog, which you're more welcome to write. But the general notion is you just need some foreign key that connects your nodes to your chunks, right, or to your vectors, and then you just go back and forth depending on what your applications. You do go back more efficient part. But it depends on what you're trying to do, right? So the basic premise is okay. So for example, if you're starting from a natural language interface, like you're in a chatbot or whatever, right? Like Lucata's fix, you're going to do some embedding, and then you're going to query, go back to the database. You're going to find that function that is most relevant, and now that is your starting, right? And now you're going to the graph, right? The question was okay, what are you doing in the graph? How are you going to generate the query that you're going to get from the graph? Once you've gotten to this one point where you have 2 or 3 nodes that are interesting to you, is that enough? You want to get more? How will you get more? Maybe you have semantic content in the graph that you want to use on. And again, that's exactly where it really depends on your particular use case, whether or not you're going to go jumping back and forth to make sense at all for you or not. Right? That's kind of the trend.
Can I ask one question on that graph? How can you add more context? And I say context not to vector embedding point, but in the metadata case. To almost traverse the vector search a little bit much more intelligently, right? With the metadata filtering and everything. Yeah. If the graph knows, then the that we would have to say, is there a viable option instead of maintaining two databases or
So are you asking like whether or not it's
are you pack enough information about the data itself in the metadata?
and the nodes? So the question is not only how the information is stored, right? So like you could theoretically say, hey, like I have a node like attached to this chunk, and there's a relation between this node and 5 other nodes, right? But the question is like, what do you want to do with it, right? So if you just want to know, hey, give me like all the relationships this particular node has, and that's it. That's all. And I'm not, right? Like then that's one world maybe you don't need the graph database at all, right? But if you want to say things like, find me a path between this node and some other node, right? I found these 2 semantically related things, right? But I want to understand how they connect up, right? That's where you're going to want a graph database, right? To be able to do these more complex queries.
I have a suggestion because we have some food left and we all 4 of us are here to talk. So instead of trying to squeeze this to one question at a time, how about we just start talking like one-on-ones? You can pick whoever of us you want to discuss things with, and we happily answer your questions.
Yeah, and we also have Haru back.
Yeah.
Some of us are going to just still plant ourselves there just to make it so that it's easier to talk for some people. But yeah, drug food.
Thank you so much.
Yeah.